Welcome to one of the videos in our series on signal processing systems. This video is being developed as part of our project on embedded systems design optimization, which is being sponsored by the National Science Foundation. In this video, we're going to look at the modeling of signal processing systems. We're also going to look at data flow scheduling techniques and implementation methods that are related to these techniques. First, let's start by looking at models of computation.
Signal processing systems are a very different type of computation than what we might see in a laptop system. Signal processing computations are performed iteratively on a stream of data, and we assume that stream of data is infinite. Now, we know in the real world that communication systems don't last forever, but for purposes of modeling the computation, we assume that the stream of data has no end. Signal processing systems often execute at multiple different sampling rates. These multi-rate systems are significantly harder to compute because we need to balance operations happening at very different rates. The control flow is largely deterministic. That helps us design these systems. And we have to make sure that we process results on deadlines. Meeting deadlines is critical to maintaining the integrity of the output of the signals. We have hard real-time speed requirements that may include latency, time from input to output, as well as throughput, how often we produce results. We need to predictably satisfy real-time constraints. We need to predictably take inputs, predictably generate outputs. We often have a limited amount of memory, and so we have to synthesize code that requires limited amounts of memory for both code and data. We may need to take into account partition data systems that may exist for performance reasons or for implementation cost reasons. The memory may be on-chip, it may also be off-chip. We're concerned about power consumption and energy consumption, both peak power and energy per function. And as with most embedded systems, we're worried about cost, both design cost and manufacturing cost. We're often concerned with time to market as well. How long will it take us to design the system and make sure it works? Time to market is an important reason to move to more abstract programming languages and synthesis of our code.
Models of computation are an important concern when developing domain-specific design methodologies, such as one for signal processing. A model of computation provides semantics for the interaction between the functional modules in a system. And this model, the model we choose for this, has a great influence on all the significant design processes and associated with developing implementations. These include the specification of the functionality and the system that we're designing, and simulation of that functionality, and the potential for formal verification techniques that can prove certain important properties. Certain models of computation support these formal verification techniques better than others. And also, similarly, the model of computation defines what kinds of implementation and optimization methods we can use to realize, to derive efficient realizations for these systems. And also, it describes what may be the most natural or most efficient interfaces to the environment or external systems with which the computing system will operate. And the model of computation also places constraints on the design of specification languages or programming languages for developing applications. And it ultimately influences the way designers think about applications. And ultimately, models of computation, because it has such a strong influence on all of these key aspects of the design process, it's a very important area for innovation in domain-specific design. It's important to choose the right model of computation when developing a domain-specific design tool, and also as challenges arise and new kinds of capabilities need to be developed, it's important to revisit the model of computation to see if modifications or refinements are needed to it to address those new challenges. Models of computation are used widely in embedded systems because they provide a systematic way to link the computational characteristics of these systems with key characteristics of the applications that are associated with different types of embedded systems. So in these model-based design methodologies for embedded systems, high-level application subsystems are specified in terms of components that interact through formal models of computation. And the components themselves can be specified internally using existing platform-oriented languages. And there's a wide variety of these languages, which are very important in connection with certain types of platforms. Languages like C and Verilog or VHDL for hardware design, or Java, for example, as another important language that might be useful in developing components for some domains. So there's a great deal of flexibility in developing the internal implementations of these components, while the interactions between the components are governed by the models of computation that are associated with the particular model-based design environment. And at the same time, object-oriented techniques can be used very productively in many model-based design environments as well. The principles of object-oriented design are very complementary to those of model-based techniques. For example, object-oriented techniques can be used to maintain libraries of components so that one can, for example, enhance the code reuse across components that have related functionality. And there are a variety of popular models of computation that are used in different kinds of embedded systems. Dataflow is very popular in signal processing systems, and we'll be talking more about Dataflow in this video. And Dataflow is very much related to a more general class of models called Conn process networks. So Dataflow and KPNs are used extensively as in model-based design methods for signal processing systems. Another class of models of computation are synchronous languages, which are useful in reasoning about systems that where operation with respect to certain clocks is very important, for example, in synchronous hardware design. And also continuous time models and modeling mathematics associated with different types of continuous time mathematics is also important in various application areas, such as in integrating issues related to the stability of control systems that are designed. And discrete event models is also another class of models that can be very useful, for example, for modeling interactions with networks where packets can be modeled. The arrival or departure of packets from a node can be modeled in terms of events. And finite state machines and related formalisms for control are also very useful in a variety of application domains. So as you can see, there's quite a diversity of different types of models for embedded systems. And among these, we're focusing on Dataflow and KPNs in this video because of our orientation here towards signal processing systems. To appreciate what's distinguishing about the Dataflow model of computation, it's useful to review some key aspects of the imperative computing model, which is the computing model that's associated with conventional languages like C or C++ or Java. We also refer to these as procedural programming languages. So in the imperative computing model, we have the notion of a central processing unit, or CPU, and one major component of the CPU is what's called a program counter, which contains the address of the next instruction that's supposed to be executed at any given time. And this instruction is part of a large set of instructions that make up the program within some area of memory, which we call the program memory. And as the program executes, it manipulates data, which is stored in data memory. As the program executes, the program counter is directing which instruction is to be executed at any given time. And part of the execution of the next instruction also determines what the next instruction will be by its modification to the program counter. And so in the imperative computing model, we are specifying not only what functions are going to be computed through the different instructions that are used in program memory, but we're also specifying the exact order through which those instructions are going to be computed, because we are specifying as part of the program how the program counter is going to be manipulated throughout the execution. So you can view this as a control-driven model, because deeply embedded in the program is the manipulations to the program counter, which is determining the flow of control throughout program execution. Next, let's consider modeling DSP systems. So when modeling embedded signal processing systems, it can be very helpful to depart from this kind of control-driven execution. And instead, it's useful to examine some of the key aspects that need to be taken into account when we want to develop a model when we rethink the model of computation that we want to apply in the context of signal processing systems. So one of the important aspects of this is that we have a lot of repetitive computations that need to be carried out. And this relates to the property of signal processing systems that I described earlier, where these systems describe computations that are iterated over and over again on indefinitely large input streams. So we want to somehow capture this notion of repetitive computations in some convenient way and some meaningful way that allows us to analyze and work with these kind of repetition patterns. Also, the different components in a signal processing system have a kind of stream-oriented communication with them, where data passes along sequences from the outputs of computations to the inputs of other computations that use that data. And also, as I mentioned earlier, the signal processing systems have largely deterministic control flow, so we would like to use models of computation that can capture this kind of deterministic behavior when it exists, so that we can exploit it to improve the predictability. And as it also turns out, exploiting such determinism can also increase the power of the kind of optimization techniques that we use. However, even though the control flow is more manageable perhaps in signal processing systems, the data flow can be quite complex and heterogeneous. For example, it's common to have feedback loops in many types of signal processing systems, where the output of some subsystem is fed back to the input of the same subsystem to influence the future evolution of the computation in that subsystem. And also, there can be significant parallelism at arbitrary levels of abstraction in these signal processing systems. And we want to be able to capture that higher level parallelism as much as possible. The existing computational platforms are very effective at capturing and exploiting low-level parallelism. But in signal processing, we often have parallelism that's inherent at much higher levels of abstraction, and we want to be able to capture that and exploit it effectively through the models of computation that we use. And another aspect of the complex data flow are the use of multidimensional computations on data structures such as images or video streams, which are respectively 2 and 3-dimensional, and there are also higher dimensional types of signals that arise in signal processing systems. And this kind of multi-dimensional processing needs to be incorporated uh, strongly into the models of computation for them to be effective for broad classes of signal processing systems. Also, algorithm designers who develop algorithms for signal processing systems often think in terms of signal flow block diagrams. So they think in terms of these block diagrams where you have signals flowing through the blocks, and the blocks here represent various kinds of computational transformations on the signals, and the connections specify signal paths between blocks. So if we can develop or use models of computation that somehow have correspondence to these kind of signal flow block diagrams, it can match the algorithm designer's intuition and enhance the usability of these tools for algorithm designers. And in these individual blocks within the block diagrams, the computations have largely predictable behavior, which is what we described earlier in terms of the largely deterministic control flow. So the blocks themselves have predictable behavior. However, the way they're manipulating the data and how that data is flowing through the system can have a lot of complexity or heterogeneity associated with it, like what we described, the feedback loops and giving rise to different forms of parallelism, and also the multidimensional aspect of the data that's being manipulated and passed throughout the system. Data flow scheduling is the process of determining when operations are fired.
When we synthesize code for our data flow graph, we need to do two operations. We need to assign actions to processors, something that's occasionally called allocation. We also need to order the operations in subsets of actors that share common processors. Processors, any kind of hardware resource that executes an actor and can execute multiple actors. The objectives of scheduling include exploiting parallelism, managing our buffers, minimizing power and energy consumption, or managing thermal constraints. Here's an example. Here we have operators x, y, and z. We have one token between x and y. We fire y, that consumes the token at its input and generates one token at the output. We fire x. X generates two tokens. Now we have two tokens on the first edge and one token on the second edge. We fire z, that consumes the token at its input. We then fire y, which consumes one of the tokens at its input, leaving one other token still on the first edge. And now we fire z again, and it consumes the token on the second edge. So let's look at some properties of this schedule. We can write this schedule briefly as y, x, z, y, z. This is a sequential schedule. It executes on a single processor. We do one operation at a time. This is also a periodic schedule because it produces no net change in the buffer state. The state of the buffers at the end of the schedule is the same as the state at the beginning. That is, at the beginning and the end of the schedule, we have one token on the left-hand edge and no tokens on the right-hand edge. That's what makes it periodic. It is a static schedule because we don't need to determine anything at runtime. We know absolutely at each point in time what needs to happen. For many data flow graphs, we can have multiple schedules that satisfy the data flow constraints. The number of different schedules for a graph can grow exponentially with the size of the graph. Different schedules generally provide differences in latency, in throughput, resource requirements, code size, and the requirements for data memory. For an important and well-defined set of data flow graphs, the different schedules for the graph produce the same results. This is known as determinacy, and this has been demonstrated in a couple of different important papers. Designers can experiment with different alternative schedules
while leaving the actor implementations intact. Designers can also change the actor implementation under a certain set of well-defined rules that leave the schedule intact but provide for different implementations. Other schedules, here's our example, other schedules that satisfy the data flow constraints include X, Y, Z, Y, Z, X, Y, Y, Z, Z, X, then two Y's, followed by two Z's, NX, followed by two NY, followed by two NZ for any N, and X, followed by two NYZ, and there's others as well. You'll notice that in all these schedules, the unit of repetition executes X once, Y twice, and Z twice. That makes sense because we know that X generates 2 tokens for each firing. Y and Z each consume 1 token per fire. A data flow graph gives us several opportunities for parallelism.
Let's step back and consider the complete implementation process.
In task parallelism, we have 2 different operators executing on different hardware units. In pipeline parallelism, we have 2 different copies of the data flow graph, each with its own data, executing in different stages of execution on the hardware. We can also identify data parallelism, which depends upon other characteristics of the data flow graph that we haven't covered at this time. Here is a design flow for implementing our data flow models in either hardware or software. We start with the data flow graph application. We then perform some graph transformations, and we analyze the graph to determine some important characteristics. We apply scheduling algorithms and also buffer management. This is guided in part by a library of actors and also a library of communication operation. The result is a graph level function and implementation that we can validate, and that can be, the result is a function level implementation that we can create in either hardware or software so that we can execute it on, for example, an FPGA in the case of hardware, or a GPU or a DSP in the case of software.
In summary, data flow modeling is very effective at capturing the application characteristics of signal processing systems. And at the same time, data flow models give us a great deal of freedom in deriving implementations that can be streamlined for various objectives. Thanks.